Welcome everyone. I'm Jalal Khalil, a PhD student from the Computer Science Department of the University of Alabama at Birmingham. Today I will give a presentation on our system paper titled Realistic Urban Traffic Simulation with Ride-Hailing Services, a revisit to network kernel density estimation. First, let us look at the problem we study and the motivation for this research. Ride-hailing is a service that connects passengers with drivers. Uber and Lyft are two applications that provide ride-hailing services. However, little is known about to what degree their operations impact urban traffic, since these companies seldom share their ride data due to privacy reasons. Ride-hailing helps solve the first and last mile problem. It's also favorable for short trips such as those to the airport or restaurants. However, studies have shown that ride-hailing services increase congestion in big cities. Our solution to study the impacts of ride-hailing services is to build a digital twin, which is a transportation simulation model that incorporates all kinds of transportation modes. This digital twin allows us to analyze the impact of ride-hailing services under different scenarios. For example, it enables researchers and decision makers to answer questions such as, what will be the impact on traffic if the number of Uber drivers doubles in Birmingham, Alabama? In this research, we use ACM and agent-based simulation software to run the simulation. Different input files are needed, such as the travel plans, the initial locations of Uber drivers, and the underlying road network, from which ACM conducts the travel simulation to generate traffic statistics and reports. As an overview, there are 5 main steps to build the digital twin. First, we collect Uber trip screenshots from Uber drivers' smartphones. Second, we use crowdsourcing to extract ride information from the screenshots. Third, we fit location distributions from the extracted ride data by network kernel density estimation. Then, we create population day plans by sampling from distributions that we learned. Finally, we run simulation using the generated day plans. Our team recruited and met with 8 Uber drivers who agreed to participate in our IRB-approved survey. We choose to survey drivers rather than passengers since their ride data are more diverse. We motivate the drivers to provide trip screenshots by giving them an incentive reward. In total, we collected 4,229 screenshots. After we collected the screenshots, we recruited 155 students as crowd workers to help extract the ride information from these screenshots, using proper quality control techniques in crowdsourcing. Specifically, crowd workers extracted text information manually. The information include origin address, destination address, duration, and time requested. Notice that the origin and destination addresses are just street names, so the exact location can be anywhere along the street. Fortunately, there is also a thumbnail image that provides an approximate trajectory on a map, so we can utilize it to recover the exact origin and destination locations. This is achieved using an online tool called Georeferencer, which will illustrate its usage here. First, a crowd worker uploads a screenshot which will appear on the right-hand side of the screen. A map is also shown side by side on the left where we can zoom into our study area. We can then find reference points such as turns of highways or the corner of a park to align the screenshot image on top of the map. Here is the overlay result with the screenshot image changing its transparency. Once the screenshot is overlaid on the map, a crowd worker can verify if the blue trajectory of thumbnail image matches an actual path on the map. Then he or she can zoom in on the green source circle and red destination circle to find the actual pickup and drop-off locations on the streets with the proper names. A crowd worker also chooses a few critical points on the trajectory to obtain their coordinates. Note that right now, a trajectory is just an ordered sequence of timestamp points. We then use map matching to recover the actual route of the trajectory on the underlying road network. In this figure, we see a sequence of 6 points annotated by a crowd worker. Here is a sparse trajectory before map matching that connects the points together. Notice that the line is not mapped to the underlying network. After map matching, we get the green route, which is mapped to the underlying network. We only keep the green route as our extracted trajectory for an Uber ride. We plot the trajectories to obtain a heat map where we can see that highways in the downtown Birmingham are the heavy hitters for Uber rides. We also made a tool to visualize the OD matrix that indicates how many Uber rides go from one zip code area to another zip code area. As we can see on the right side, we have the option to zoom in or out and filter by the number of outgoing trips. Now that we get the trajectories, we want to use their pickup locations to fit a distribution on the road network. We also do the same to learn a distribution for drop-off locations. These distributions will later be used to generate realistic day plans for Uber rides. Our solution is to use network kernel density estimation, or network KDE, which generates a probability to sample locations so that the locations are on the road network and respects the observed data distribution. Xie and Yan were the first to propose the concept of network KDE, and to reduce computation cost, they discretized road segments into small units, called lixels. Later, Romano and John extended this idea along the temporal domain to cope with the spatio-temporal network KDE. However, these solutions do not guarantee that every sample contributes equally to the road network space. For example, consider a Gaussian kernel with a standard deviation being 10 meters, and we ignore the small amount of density beyond 2 standard deviations. The figure on the left shows the spaces impacted by each sample, and the figure on the right shows the same thing after the road network is discretized into lixels. If we denote the probabilities in 1 standard deviation by A and in 2 standard deviation by B, then the contribution of sample x1 to the road network is 2A plus 6B, which is beyond 1. In contrast, the contribution of sample x2 is just 2A plus 2B, which is less than that of x1. This violates the requirement of KDE that samples contribute equally to the total space. We propose 2 solutions. One is to distribute the density evenly among locations of the same distance to sample. For example, now each green branch contributes only B over 3 instead of B. Another solution is just to normalize the lixel weights for each sample so that the total weights sum up to 1. Here is the distribution of pickup locations fit by our second solution. To obtain the spatio-temporal network KDE, we also need to consider the timestamps of pickup and drop-off locations during fitting. With time slots, lixel now is called a rexel, following the terminology from existing work. For example, if an Uber pickup occurs at 8:20 a.m., we distribute the weights to the 3 hours centered at the 8th hour of the day, following a one-dimensional Gaussian distribution along the temporal dimension. Here, we visualize our spatio-temporal KDE distribution around UAB green, which is fitted from timestamp pickup locations from our Uber driver survey. Recall that we have the OD matrix for Uber rides from the origin zip code area to the destination zip code area. However, our data is still sparse, and some zip code area pairs may not be covered. Therefore, we use the background population data for smoothing, where the population number from each zip code area can be obtained from American Community Survey. We set the smoothing factor alpha as 0.8. Once we obtain the smooth OD matrix, we can multiply every element by the total number of Uber rides, so that each element indicates the number of Uber rides to generate from one zip code area to another. This slide illustrates how we generate Uber rides from our learned distributions. For example, we need to generate 3 rides from zip code area 35204 to 35209. To generate the pickup location, we sample from the AirXL distribution for pickups inside zip code 35204, and then sample a time following the temporal distribution on the sampled lixel. We can then sample the drop-off location and time using the AirXL distribution for drop-offs. but we only sample from those valid drop-off axles whose time is not before the sampled pickup time and not more than 1 hour after the pickup time. Once we generated the Uber rides, we integrate it with our background traffic, which is generated from another user survey and open data repositories in our prior work. We also include bus trips in our study region as an alternative mode for passengers who do not drive their own cars. These day plans are then inputted into MATSIB for transportation simulation. We explored the impact of the number of Uber drivers using our simulation. We find that 400 Uber drivers is sufficient to clear all requests in a day. We also noticed that having more than 400 drivers does not help, since many drivers are not occupied when there are 800 drivers. We also explored the traffic difference when there is no Uber ride as compared with Uber rides with different number of drivers. We can see that Uber rides are not increasing congestion in our study area, and even increase traffic volume in some hours, likely because of the reduced traffic by car sharing. Here we show a visualization of our simulation as well as the rides taken by the first Uber driver. Thank you for your attention.